I'm a research scientist at the Center for Urban Science+Progress, New York University. This is my first time at XLDB, and it's really a true pleasure. I learned a lot today. So I got a PhD in computing, which is pretty much in visualizations and big data. And before I moved to New York, I worked mostly with scientific data, like simulations from national labs, things like that. When I moved to New York, I was exposed a lot to urban data, and I was really intrigued. And it's been like my great passion in the past couple of years. So today I'm going to talk about visualizations, big data, and in the urban context, right? So some background about Cusp. So Cusp is a public/private data research center within the NYU. So our aim is actually, work closely with the city agencies together, so we can actually look at the data the city produce and understand the city and improve its performance. So the issue is that a lot of agencies inside the cities, they have their own proprietary data. This is excluding from the open data source. They store data, they've been collected for a very long time, but they don't really have the resource or the platform to share with other department or agencies to bring people to do analysis. So our vision to actually make Cusp a secure place so the city agency can deposit data together with our research partners, so we can bring in researchers from different backgrounds, different disciplines like transportation analyst or civil engineer or economist, working closely with computer scientists to look at these data at scale. So that is said, we would like to treat New York City as a living lab and learn about the cities and then apply what we learned here to other cities throughout the world. Maybe we have partnership with people in London, Toronto, so on and so forth. So we have a lot of collaborations in the academic space. University-wise, we have CMU, University of Warwick. And in industry, we have AT&T, Microsoft, Xerox, and also national labs like Lawrence Livermore and Brookhaven National Labs, so on and so forth. And we do have a master program at Cusp that train the student in different backgrounds. This is a professional master program from different backgrounds to actually have a skill in look at the data science in the urban area. And so my responsibility at Cusp, there's twofold. So first on the production side, I'm actually the chief data scientist for the data warehouse infrastructure, actually overlooking the data intaking process. But I'm not going to talk about that part today. So on the research side, I'm a researcher working to promote visualizations and big data, working closely with the domain scientists to help them analyze the data they have. So the motivation, why do we care about urban, right? So actually, I don't think I need to say this because we're already here. So just a few remarks. The world is urbanizing and really fast. So half of the world population now lives in cities, and that number is expected to be 80% by 2050. And in fact, in North America, that number is already 80%, and that will grow to 90% in the next 40 years. So this is fast growth in urbanizations will lead to a lot of challenges in transportations, pollutions, housing, as you can see so far. But one thing that we usually said at Cusp is that cities are the source of our problems, but it's also where we're going to find the solutions. And the great news is that in this urban environment, we can collect a lot of data. There are a lot of them are available, either through the mobile device, through the sensor network, or through the city agency, how they collect them like that. So we can actually take these opportunities to understand our city better and actually derive solutions. But in order to do that, we would have to stepping through, the hurdle of big urban data analysis, right? So what I mean by urban data, so pretty much any data generated inside the cities or about the city is urban data. But at Cusp, we put them in three bins. The first one in the organic data flows. Pretty much anything you put on the Excel spreadsheet, could be like tax record or parking tickets or noise complaints, things like that. We treat them in the first bin. The second bin are those sensors that could be from your mobile phones or for social network as well. And the last bin is actually on the novel sensor technologies. So these work as a top-down, for example, like LiDAR technologies. Or at Cusp, we do have an urban observatory facilities where we put cameras on top of those high-rise buildings, and capturing all of the energy usage throughout the cities. So when through the window we see the light turn on and off, we're actually monitoring how they use the energy, things like that. So Cusp is aiming to actually integrate all these type of data and perform analysis, not just on records, but also on imaging, videos, things like that. And about big data, so actually, the definition of big data is that we already know about the 3 V's, and now it's going to like 4 V's, 5 V's, and 7 V's, with visualization also included. So I think the definition for big data is also getting the big definition now. So at Cusp, we try to simplify the definitions, right? So what we call big data is anything that's, where we have new data, new type data, or new size of data, that is making it really challenging for us to use the current technology or current techniques to analyze it. We brand it big data. So I mean by that is that if we look at a number of examples here, for example, if some of our scientists work on some model in an Excel spreadsheet, now they have more data. The Excel couldn't handle anymore. We call it big data problem. Now our civil engineering folks, they load data on ArcGIS to do their urban planning, things like that. And now they have taking forever, like an hour to actually do linking different data layers because of big data problems. Or in the complex type, for example, if we do visualizations, now, for example, we want to render the cities. We want to put shadows, cast shadows on the cities. But now there's so many level of detail, so many details of the buildings, making the process of casting shadow is really slow, really inscalable. We also call it big data. So to us, those are big urban data problem. But the thing is, big data is not new. Since I work in the scientific computing communities, it's been there for quite a while. Like 30 years ago, in the national labs, they do simulations. They run things on really large cluster of machines. And then so the large body of work in distributed system, database system, things like that, right? But the thing is that back then, the data were in good hands. I say it that way because the data was stored in the national labs. They have the group of people that have expertise in parallel computing, and they have the infrastructure there. They have very expert in their domain, all working closely together. So that wasn't really the problem there. But now the data is so easy to fetch. We can actually go to NYC Open Data or Data SF, and pretty much in an instant you get like 100 gigabyte data in no time. And now the owner of the data is actually data enthusiasts. They don't really have the background to doing data analysis. So that is the challenge now. So the final goal is try to transform data into knowledge. And this is the same concept of data science, right? So this process is very complex. It needs expertise in different areas. It could be database, provenance, visualizations, machine learning, statistics, so on and so forth. And there's just no way a single person can know all of this and look at the data and do data analysis. This is a really complex process. That's why it's there, regardless it's big or small. So our goal, our aim at Cusp is try to build a platform, data applications, such that we can encapsulate all of these techniques together and bring it to the data enthusiasts so they can look at the data, load all data, and do analysis. So that's actually the aim of my line of research. So this type of application, these type of tools have to be able to do some tedious tasks like data cleaning, data integration, load data, ETL, a little bit ETL, and have to guide the user through the exploration process. And the tool has to be able to be used by non-expert users, like social scientists, citizens, or government employees. And of course, when human in the loop, visualization is very important because that's the most effective way to communicate with a human. So throughout the talk, I'm going to show two examples, two applications that we built on these concepts. So the first one is on a taxi. So we know that New York City is really famous for taxi, well, the yellow taxis. But what most of us doesn't know is that we also have the green cabs, the green taxis that serve the outer boroughs. And more importantly, the data on a taxi has been collected since 2008. So whenever a passenger enter a taxi, they record the number of passengers, the location of where you started and where you're going, and what is timestamps, as long as also like the trip amount, the tax amount, so on and so forth. So it's been there for the past 7 years. And the city agency don't really know how to deal with that. But my point here is that the taxi data by itself is actually the transactional record. So because they record pretty much on the same transaction, right? But because of the spatial and temporal components of the location and time for each of the record, it actually become inadvertent sensors, which means it can tell us a lot about the city life, the human mobilities, about the infrastructures, the environment, or how people move inside the city. So here I'm showing an example. On the top, we're seeing the plot, the number of taxi pickup trips in 2 years versus time, 2011 and 2012. Just look through the plot, we can actually see when the city is full of people on the street or when there's less people on the street, no activity at all. Even though they're coming from 2 years, the red and the green, but the patterns looks very similar. right? It's only shifted by 1 day because consecutive years have shifted 1 day, the week shifted by 1. So because of that similarity, you can actually see that we can detect anomalies very easy. For example, we can see that on August 2011, there was a big dip in the number of taxi pickup. The same thing as October 2012, right? So these are, if you are from New York, you would know like what happened there, right? Because there was 2 big hurricanes. One is Irene, happened in 2011, and the other one was Sandy, 2012. That no one was on the street. And then we also see that, for example, during Christmas, there's a very little number of taxi pickup. So this is at the macro level, but at the micro level, when we plot this data onto the street, so here I'm showing the 4-hour periods when we're plotting the taxi pickups and drop-offs onto Manhattan. So the blue dots are the pickups and the orange dots are the drop-offs. So during the 4 hours period on May 1st, 2011, we see that from 7 to 8 a.m., the activities looks very normal, but at 8 a.m., the entire 6th Avenue, which is in the middle, was blocked entirely, and it came back to normal again at 10 a.m. So that was when the 5-borough bike tour happening, so they pretty much blocked the entire road. So just by looking through this data, we can actually tell a lot about the cities, what's going on inside the cities. So the takeaway from this slide, I would like to say is that there's 2 things here. First is taxi can tell us a lot about the cities, more than just the activities, and the importance of visualizations. Well, for example, without a visualization, if I just put the Excel spreadsheet here, it would be impossible for me to tell you the story. Like there was the road blockage, or there was a big drop in 2011, 2012. So the challenge actually in exploring taxi data is that there's a lot of the data. So each day there's about 500,000 trips. So in throughout 5 years, we have about almost 800 million. In the past 8 years, it's more than 1 billion trips. And the Taxi Limousine Commission agency, the one that collect the data, they don't really know how to look at this. They use Microsoft Access, but again, that's just impossible to load like a day worth of taxi data. And so when they have some hypothesis they want to confirm, they give the data to the data scientists and ask them to generate some plot. And then they go back and they see is that correct or not, and the loop continues. It's really unscalable. And the data is also complex. It has multiple spatial and temporal components. So our goal is try to build a tool to allow them to explore the data at their own hands. So the tool has to be able to have some visual components, so they don't have to write SQL code like on the left. They can actually do all the queries right on the tool, like spatial time or the space, and actually get back to something to explore through the plots at the bottom. So our goal is actually because we have like three things here to explore, right? The space, the time, and also the attributes. So that's the where, what, and when components. We would like to be able to answer like one component based on the other 2. So this is the Pelkey triad for spatial and temporal data. We follow that. For example, what is the average trip time from Midtown to airports during weekdays? That is actually, we know when, which is weekday. We can specify on the tool, the weekday, for entire May. And then where we just draw directly on the map from Midtown to the JFK airport, and then they will show the result at the bottom. So that is about 45 minutes of the trip time. So I would like to give a demo of the tool. So I already opened it up here. So right now on my laptop, there is 3 years worth of taxi data, about 30 gigabytes of compressed index data. And here I'm showing 1 hour period of the taxis. So all the blue dots are actually the pickups, and the red dots are the drop-offs. Here, 1 hour period. So if I'm moving back and forth, for example, I'm shifting by 1 hour, all interactively. You can see that at roughly at 8 a.m., there was entire road, 6th Avenue were blocked right here, right? As I show on the slide. And then here we come back at 10 a.m., things go back to normal. So now if we go further for the entire week worth of data, if I'm showing here, 96 plot. So this is for the entire week. So a lot more. And here at the bottom, we actually show the activities by day, right? So you can see the days and the night. And we also have other attributes, not just the number of trips. So all these plots, for example, like the tips amount, or the trip, or the distance, or the time, or average speeds, things like that. You can also see that at 4 p.m., there's always a dip at number of pickup, because that is when the taxi has to go back to the garage, and they wouldn't pick up the passengers unless you're going along their path. So if you go to New York at 4 p.m., couldn't pick up a taxi. This is why, yeah. So we also have the heat map, for example. So instead of showing the dots directly, we also show the heat maps. And these are the hotspot of cities. For example, these are the Penn Station area. This is the Port Authority. This is Grand Central Station. And this is just the Chelsea. All the bars and clubs and nice restaurants, so it's always crowded. We can also do, actually the main features of TextDB is we can actually do spatial queries. So here I'm showing, so this is only showing the trips starting from this Chelsea area, this region, and the plot updated. So all these are done in real time on TextDB data. I can also select, let's say, the Upper East Side here. So now showing two queries. One is for the taxi strip starting from the Chelsea area, and the other one for the Upper East Side. And the boundary color also show up on the plot. We can actually showing from one place to another. So showing all trips starting from the Chelsea area to the Upper East Side. So all these spatial temporal queries, origin and destination queries, all done in real time, which is very, very, very important for the people at the TLC or the DOT department. So I can go further. Let's query the entire year worth of taxi data. If I go in here. It will take a little while, but it's not that slow. 365. Okay, so this is actually for the entire year 2011. We can actually do reverse query. So now if we want to know people arrive at the airport, like JFK or LaGuardia, where did they go after they arrived at the airport? We can do selection like this. So I'm selecting all the trips starting from LaGuardia there, and so all the trips starting from JFK airport, right? And now if I click here, say the destination queries, I click query again here, we see these are all the places that they went to after they arrived at the airport. Now, if I actually normalize and zoom in a little bit, so these are actually the super hotspot of cities. They went the most after they arrived at the airport. So I think you might have guessed these are actually the hotels, famous hotels inside the cities. We zoom in, these are the Hilton right here. The Hilton, and we have the Marriott, things like that. So this is for the entire user worth data. So let me go back to the talk. I think I might run out of time. Okay, so what makes it so fast at the back end? So actually, there were very fast database index in the back end. We first try current databases, but the thing is that most of them is not designed for interactive visualizations. So the most challenging thing for us is that most of the queries, when you do spatial and temporal queries of origin and destination, it would take like seconds or 30 seconds to actually have those queries that I show you. But also the index and the building time take a while as well. So what we did, we built an index structure on top of current databases to make it much faster to do the queries, spatial and temporal queries. And this based on the KD trees. So we get very much an order of magnitude faster. And so I think I will skip this slide. We go through the detail of our data structure, but we also support the GPUs as well. So which means like the same, because we use KD tree, which is a very common data structure in computer graphics, and it maps very well to the CUDA 5.5 or later because they have the dynamic parallelism. So the same data structure also works on the GPUs, and we implement our our index on top of MongoDB, and we get up to 2 orders of magnitude faster in this case. So for me, just a little remarks here. So why current databases are not as efficient? For me, they are efficient, but the thing is that they weren't targeting this problem before. So they're efficient because they targeting the batch queries. Give them 1,000 queries or 1,000,000 queries, they do really fast. They get very, very small average time. But give them one query, sometimes it take a long time as well. And they also use R3 for spatial indexing, which is when you have multiple spatial attributes, that become a bottleneck. And we also make use of GPUs for the faster querying. So for me, R3 or KD tree is just a matter of which community you are from, database or computer graphics. Because for us, computer graphics, we use KD tree. It's easier to implement, and it's highly tuned for in-memory access. But for R3, it's easier for update and for on-disk access, right? So what we did here is that we make the KD trees also work for disk-based access. So we kind of fusing the benefits from both data structure. But it really depends on the application. Either R3 or KD tree can be used. The status of TaxiV is that it currently has been deployed at DOT, has been used by them. So they most of the time used for querying the data in and out of corridors. And we also apply this for different data sets beyond taxi. We also have the bus fees as well, and we also bring it to the web. So as you see, this is a prototype on the web, just exactly as I demo. And this is just for the eye candy, I guess. So here's this is another work that I work with an economist. He wants to learn about the what's the life of taxi during a day. So the blue edges are showing when a taxi has the passengers, and the red showing when they have no passengers. So you can actually see that when they have no passengers, it takes much longer time, take his time to find the passengers, and when they have one, it moves really fast. But they pretty much cover the entire Manhattan area. So for this particular taxi, he didn't even get out of the Manhattan borough, just stay inside the city. Sorry, because I think I'm running out of time, so I'll move really fast a little bit. So beyond TaxiV, the taxi data is also really rich, and a lot of attributes we can go beyond just visualization, right? So here I'm showing a prototype. We have Find a Cab app. So actually in New York, you see a lot of taxi, but when you need one, it's really hard to find. So what we did here is that we're using historical data set. We say at this particular time and day of the week, which corner of the street you should go to have a higher chance to get a cab. And this app just detects your locations and points you to the direction that you should go to get the cab. We should do ride-sharing simulation at scale. So our targeting, our aim here is trying to build the framework that can simulate different parameter space. Real large parameter space, like the numbers passenger you can share, like what is configuration of your cars, what is the requirement from the taxi vendor, things like that. And we run this on the MapReduce, the Hadoop cluster, and we can reduce simulation for the entire year in just under 50 minutes. And so our goal is actually on the scalability. We should apply some concept in the vector field visualizations for detecting the traffic that makes up the cities using the taxi data. Pretty much we're mapping the taxi data into 3D scientific data field. All right, so for the future directions, actually, we think urban data is going to go 3D, right? Because if we look at the number of challenges we look at the moment, like building informatics, when we do the checking the building energy usage, we need to know the building volumes. When we study urban heat island, we need to know how the ray going to bounce between walls of the buildings. Or we do sky view analysis. When the architect building a new buildings, look out the windows, they want to see how many landmarks that window can see, so they can really price the apartment correctly. So those type of problems in the urban area actually need 3Ds of the buildings. So we do have at the core layers, we have the mapping infrastructures from either Google Maps or Apple Maps. They can do beautiful building rendering, but when you build a visual analytics application on top of those, you don't get that nice buildings out of the API, and you cannot really integrate data on top of those layers. And also, when you want to build an application at this scale, if you use Apple Maps or the Google Maps, you have to download each tile of the map onto that screen, and each frame can take you 2 gigabytes of download to the traffic back and forth to the internet, right? So this actually showing TaxiVs on our large wall display using our own rendering system, not the Google Maps or Apple Maps. So this is actually the current work at the moment. So we build out this 3D urban GIS system. At the core, it is a mapping system. You can actually do all the mapping techniques just like Google Maps, Apple Maps. We can draw all the street network and 3D buildings. The challenging here is actually on the how to do this at a very fast frame rate, 60 frames per second, how to do all dynamic label placements, collision detections, texture shaders, things like that, and how to do level details when you have a very large scene, right? So this is very exciting for me. But actually, the real power is coming from the data integrations. So our goal is that we want the application developers can actually put in their own data, either for the road network or for the building informations. All things like that can be actually done by the app development. It's just a platform for them to do data integrations. With that, I would jump into the demos really quick. So this is actually. So as you see, because this difference is that when you see all the labels, they're actually moving and they actually do collision detection, so they don't have overlapping labels. It's just at the map, just similar to Google Maps, Apple Maps, but it's our in-house API and platform. Now we want to go 3Ds, so here's the building informations. Informations. As I mentioned, the real power is coming to the data selection. I can double click on this building. It can show me the 6 number. That's the BBL data. That's from New York, right? So these are not for rendering. These are integrated and linked back to the data backend to know that 6 number so you can do data analysis on the buildings. So it's actually, if you want to do the landmarks analysis, you can actually go to the top of the building here and see, I see this or that, something like that. So I think I'm running out of time. So this is actually the application that's using that API to build. For example, we want to study the building, let's say the building placement. So here they can compare different buildings together. Let's say the park score, the hurricane score, we overlay different data layers like the taxi or crime or noise, so on and so forth. So this application is built on top of the API. So the goal is to build an API to enable these applications. With that, sorry, I ran a bit over time. So just a conclusion, I think like analyzing urban data really need the exploration task, go beyond conformity task. And for that, we need visualization and also integration with database backend, because I think the space between database and visualization is been underexplored, and we see more than ever the need to glue the two together. And I would like to thank you to all of the collaborators and colleagues at NYU. This is a joint work with them, and also the architects at KPF. Oh, thank you.
Maybe a real quick question for Hui.
Are you using this data for any traffic management, improving traffic downtown?
Yes, so actually
the question was, are you using the data for actual traffic management or not?
Yes, so actually we work with the Department of Transportation. So they have a slightly different data from the TLC, which is the raw data from a taxi agency. So they do the cleaning and they do some aggregation. So we also work with them. Yes, we do.